Hey guys, welcome to another episode of Biochemistry at Home. Today, we're going to be taking a look at carbohydrates in this experiment entitled Jelly, Jelly, Yes Papa. Let's get right to it. So, carbohydrates are naturally occurring carbonyl groups found in plant and animal cells. These biomolecules are widely available and inexpensive, and rightfully so, as they are used as energy sources for our bodies and cell structures. Food carbohydrates are commonly consumed as simple carbohydrates like sugars, and more complex carbohydrates like starch and fiber. Pectin, an example of a high molecular weight carbohydrate, is a substance which forms gels. It is usually found in plants which contribute to its cell structure. Pectin is in fact a negatively charged colloid in an acid food substrate. When sugar is added to this colloid, pectin-water equilibrium breaks down, which then forms a fibrous network that gives pectin its known firmness, which is needed for jams and jellies. The presence of acid decreases the pH of the solution, which results in the carbohydrate chains joining together to form polymer networks, entrapping the aqueous solution. So, other factors that have been found to affect pectin gel formation are degree of esterification, effect of acylation, temperature, and molecular weight. In this experiment, however, we focus solely on how various sugar concentrations and pH levels help in the interaction or the formulation of polymer networks responsible for the strength and rigidity of the pectin solution.
Step 1. For the first part of our experiment, we need to measure 1/4 cup or 60 milliliters of sugar. For the second part of the experiment, we need to measure 1/8 cup or 30 milliliters of sugar. Finally, for the third part of our experiment, we need to measure 1/2 cup or 120 milliliters of sugar. Step 2. Measure 60 milliliters or 1/4 cup of water. Measure 18 milliliters or 0.75 fluid ounce of fruit juice concentrate. In this case, I use the plunger of a syringe to accurately measure the fruit juice concentrate. Put 18 milliliters of fruit juice concentrate, 60 milliliters of water, and 7 grams or 3 teaspoons of sure gel. Put it in a beaker or in this case in a casserole and then boil. Stir the mixture constantly over a high heat until bubbles form all around the edge. Add the sugar. Bring the mixture to a boil and boil hard. While stirring for 1 minute, be sure to adjust the heat source so that liquid does not boil up the sides of the beaker. After boiling, transfer it to a cup or a glass. Let it cool down and observe. For part 2 and 3, step 2 is just the same. The only difference is the amount of sugar to be added in the mixture. For part 2, add 1/8 cup or 30 milliliters of sugar. For part 3, add 1/2 cup or 120 milliliters of sugar. Cup A has 1/4 cup of sugar, Cup B has 1/8 cup of sugar, while Cup C has 1/2 cup of sugar. As you can see, Cup A and Cup B have high consistency, with Cup B being the most viscous. Cup A have a little gel clumps while Cup B has almost like a big solid gel clump. Cup C, although has the most sugar, is less viscous than cup A and B, but the typical gel consistency is achieved just like in fruit jams and jellies. Thus, it has lower consistency relative to cup A and B. In general, it is still sticky.
How does pectin turn into gel? One can successfully achieve gelling when pectin is cooked with an acid and sugar. Pectin needs partners, these are the sugar and the acid. That is why, in the experiment, we use apple juice with a pH around 3.5 to 4, while different amounts of sugar is also used to test the level of consistency in the experiment. What is the role of acidity in the gelation of pectin? The firmness of the gel or the actual gelation or what is termed the setting of pectin is dependent upon its pH. There's an optimum firmness that can be achieved in the jelly within a specific pH range. As we know, pH is lowered by an acid, and this lowering of the pH will cause carbohydrate molecules to form junctions, or they will bind. These junctions is what happens in the biomolecular level, but what we see as humans is the actual gelation. Why did the consistency change when the ratio of sugar to pectin is changed? First, let us explain what sugar does when cooked with pectin. The sugar, or the sucrose, is the one that will increase the junction formation or increase the strength of the gel. How does it do this? This is because sugar is a nonpolar ionic compound and it attracts the water from the pectin using its many functional groups. It forms a hydrogen bond with water. Therefore, the sugar molecules, when forming hydrogen bonds with water, are pulled from the sugar clumps, and this implies that the solute or the sugar and water bond is stronger than the water and water bond. With this, the absence of water, the pectin molecules are more likely to form networks, therefore becoming more firm or gelled. Thus, sugar prevents crystallization and also holds the gem's color and flavor. In connection with our experiment, cup C is the most viscous among cup A and cup B. This is because pectin, when cooking pectin, it lies in a delicate balance among its factors, which includes sugar to pectin ratio and other factors like temperature and boiling time. First, let us discuss cup B, which is the most viscous. However, it is used with the least amount of sugar. Depending on the explanation of sugar earlier, cup B should have been the least viscous. However, in our experiment, it is the most viscous. This is because of the sugar to pectin ratio. Despite the low amount of sugar, there is high amount of pectin, meaning the sugar to pectin ratio is incorrect. The high amount of pectin is not proportionate to the low amount of sugar, and this leads to the extremely firm or gelled jelly in cup B. It is smooth and it is clumped in a one big piece. Next is cup A, which is supposed to be the normal sugar level. That is why it is in the middle. It is less viscous than cup B but more viscous than cup C. The same mechanism applies in cup A as well as in cup B. The same thing happened. However, factors like boiling time and temperature can be attributed to cup A. That is why it's a little bit different with cup B. When boiling in a long amount of time, water is evaporated. That is why the carbohydrates form or junctions leading to a firmer jelly. And of course, as you add more heat, more water is evaporated. That is why cup A is also viscous than cup C. Lastly, the cup C, this is when the ratio of sugar to pectin is just right. That is why, as described in the last number, it has the typical jelly or jam consistency. Despite its high sugar content, it is proportional to the amount of pectin. Thus, this prevents the crystallization, not too firm, but this amount of sugar is not too high that it forms precipitates. That is why you can still spread this particular gel. Lastly, cooking pectin therefore needs a delicate balance of 1% pectin, 3.2 pH from the acid, and 55% sugar concentration.